Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Peter Madsen. Currently, I lead the ML Metrics team at Google. I co-founded and I'm president of ML Commons, mlcommons.org. And I co-founded and was the general chair of the MLPerf benchmarking consortium that preceded that. My research focuses on understanding machine learning models and data through quantitative metrics and analysis. I'm also an ACM member. For more on my background, there's a bio widget on your screen that will tell you everything you want to know. For those of you who may be unfamiliar with ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources to bolster your skills and enhance your career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize and Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using the technology that enriches our lives and advances our society in the digital age. Before we get started, I need to mention a few housekeeping items shown on the slide in front of you. If you are experiencing problems with the slides or audio, please refresh your browser or close and relaunch the presentation. If you have questions during this talk, please type them into the QA box at any time and click Submit. I'll be organizing the questions as Grigori gives his talk, and I'll try to get to as many of them afterwards as possible. Please be aware this session is being recorded and will be archived. You'll receive an automatic email notification when it becomes available. And you can check out learning.acm.org for updates on this and other coming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our tech talks. You may also open the link to the survey at any time from the resources window. You can use the widgets at the bottom of the panel to share the presentation link, as well as tweet comments and questions using the hashtag ACM Learning. We'll be watching for tweets. Also have a community discourse page to continue discussion after the webcast, including questions we can't get through. So with that, let's get to our main event. Today's presentation is reproducing 150 research papers and testing them in the real world by Grigori Fursin. Grigori is a computer scientist with more than 20 years of experience pioneering novel auto-tuning, machine learning, and knowledge-sharing techniques to modernize the development of efficient software and hardware. Grigori was a tech lead in the EU MILEPOST project with IBM, developing the world's first ML-based compiler. He was a senior research scientist at INRIA and co-director of the Intel Exascale lab. He's a recipient of the ACM CGO 17 Test of Time Award, the INRIA Award of Scientific Excellence, the EU High Peak Technology Transfer Award, and several Best Paper Awards. Grigori is president of the C-Tuning Foundation and the founder of the CKnowledge.io platform. He's an active open source contributor, educator, and reproducibility champion, notably through his involvement in the ACM Task Force on Reproducibility, ML Commons, and artifact evaluation. He's the author of the Collective Knowledge Framework to bring DevOps and FAIR principles to research with the help of portable, customizable, and reusable workflow templates, reproducible experiments, and auto-generated live papers. Grigori's mission is to bridge the growing gap between academic research and industry by helping researchers share their novel techniques as production-ready workflows that can be quickly validated in the real world and adopted by industry. I just want to say that I think we often think of ML as being an incredibly advanced field, but it's really in its early days. It's really more art than science. And it's folks like Grigori and the work that he's doing that will help us turn it into a mature engineering field and really unlock its potential to help everyone. So I think it's fantastic, the work that Grigori is doing. And with that, Grigori, let's take it away.
Cool, thank you. Thank you, Peter, for the introduction. So just a brief outline for my talk today. So I actually want to spend some time describing some of my first projects, research projects, when I tried to bring machine learning to design efficient systems. And the reason is that many years ago, I faced really many problems, reproducibility issues and so on, that kind of blocked my research. And at the end, I had to kind of sacrifice my research and switch to solving all those reproducibility issues. And I'm not regretting this, because at the end, I started working with different conferences, trying to introduce reproducibility initiatives at machine learning and systems conferences. It worked out very well. And in the past years, past 5 years, I spent I was very closely involved in reproducing, by today, 150 research papers. And I want to tell you about this experience today, and also what I have learned and some tools which we developed to actually automate this process and make it easy for researchers to test their techniques in the real world, which I think is really missing at the moment. And then I'll spend some time actually describing some of the potential tools which can help with that, and some real use cases which I was involved in. But just starting, I just want to get a funny story that my very first research project was back in '96, and it was a summer project where I remember that I was an undergrad and I was very interested in robotics, machine learning, physics, electronics. And I saw this project, summer project, which was saying that let's try to reproduce one of the papers on, there was one of the second or third waves of interest towards neural networks. So we wanted to reproduce a Hopfield neural network and try to test it in production. And for those who don't know, this network, it basically can learn some characters, and if you have a noisy characters, it can restore them. And it can be used in cases like post office, where you can actually scan characters, and if they are noisy, you can improve them. And I thought, oh, wow, it's a nice project, 3 months project. What can go wrong? I'll just learn new things, and it will be very easy and interesting project. What I didn't realize at that time that obviously there was nothing shared with those papers. So we didn't have at that time code, we didn't have shared data sets, we didn't have automation tools and so on. So it was my task to build all that. And I saw it was fun. This summer I started preparing data sets. I implemented one of the models in C. I did all the training frameworks. I started programming in Bash and C to perform validation and so on. Suddenly, I realized that it was taking too much time, so I had to parallelize code. It was crashing all the time, so I needed to look at how to improve fault tolerance. I realized that we have to keep track of all the experiments. By the time I started getting first result, it was way beyond 3 months. And it wasn't a problem because I decided to keep on working on this project in my spare time, because really it wasn't my research, it was just a learning curve. It was fun. But when I started getting first results, they're not matching the paper. So I had to debug the code. When it started working and we got some results and accuracy was matching, I just realized that the code which I wrote was too slow for the production. So I started also realizing that the data sets in the real world was not matching. So I had to find better data sets. I had to optimize the code matrix multiply in assembler at that time. We realized that it's also very long. So I decided to see if maybe we can implement it in semiconductor. I spent some time writing my own simulator, getting tools done. And by the time this 3 months project turned into a 3-year project, and at the end, I kind of did the work, but we couldn't use it in production because, first of all, the whole implementation was just way too expensive. And at the same time, it was not fast enough. And we didn't have realistic data sets, and we needed further optimizations. Now, at that time, I was young, so I thought, okay, what can I do? Let's do a PhD. And I thought that in 3 years, I will solve all the problems in the world. I will become famous, get back to machine learning, and enjoy life. Unfortunately, what I didn't realize is that first thing what I wanted to work on for my PhD was to improve the efficiency of computing systems. That's what I saw that was the weakest link at that time. And one of the things what I saw optimizing matrix multiply manually through assembler is that we really need a better compiler, so they're not doing a good job. When I started working on optimizing, improving compilers, I suddenly realized that the problem is actually really deep, and there is a fundamental problem why I solved those problems with my first project was that the way how hardware and software is developed is that we have to whenever we develop a hardware, we use some limited number of benchmarks and datasets because it's just too time-consuming and costly, and they're really not often representative of the real world. It can take years of development. Then when it's ready, we throw it on a compiler team usually. Compiler team is trying to fix optimizations. By the time it's ready for the production, we suddenly realize that the real work was actually really not the same as they were used for developing hardware, so compilers are not doing a good job. Then we do research. Researchers are spending lots of time on trying to look at few benchmarks and datasets which are not really necessarily also representative of the real world. We publish papers, and by the time we publish papers and fix few things, a new hardware is coming out. New compilers are available. And this is a vicious circle which was there for 20 years and was really, it had to be solved somehow. Okay, by the time I started thinking that, I saw that auto-tuning was very popular at the time, so ASPLOS library was showing good improvements. If you empirically look at different optimizations, and you can actually get really good results of matrix multiply and improve it by 10x. But then you realize that it's a very slow process. So, and what is worse is that it's only 2 transformations which you can apply to code. But if you look at the compiler, that over years, the complexity was growing tremendously, and from 10, 15 optimizations, Boolean or parametric available in 99 in compilers, we got to 200, 300 optimizations by 2017. So the complexity was growing, and it wasn't, we couldn't actually make it practical, the auto-tuning in compiler. Just going quickly, few more things about the research which I was doing. Okay, what can we do with that? So we started thinking about improving, looking at the auto-tuning inside the compiler, and indeed we could really improve the performance of the compiler and performance of program with long auto-tuning, but once again, it was really too slow to be practical. And at that time, I started thinking about if my original research was looking at building better systems for machine learning, why not use machine learning to improve the efficiency of computer systems? And again, just for those who are not familiar with that, the idea was pretty simple, is that if you have many programs out there, infinite number of programs, that maybe we can actually find similar programs, and similar programs will have similar optimizations. So in such case, if we can find some kind of program features or embeddings and use hardware counters to characterize programs, then we can use standard machine learning to predict optimizations. And at that time, that's how the MILEPOST project started. In 2006, 2009, the idea was to test this idea in the production compiler. And once again, having my background in building tools, I was responsible for actually building the infrastructure for this compiler. What happened at that time is that 80% of my time I spent not on innovation, but on actually again assembling data sets. There were not enough data sets. We started improving compilers. We started building infrastructure for training and so on. There was a great work with IBM on extracting features from the program. We published nice papers, as always, and we showed some nice results that you could have 87% accuracy on predicting compilers, predicting optimization compilers on a few benchmarks. But then the question came into, can we actually test it in the real world? And my idea was to implement this machine learning model inside GCC so that we can share it with the world and test it inside real systems. And the idea was to get this, so that's when I created ctuning.org. Basically, it was a database connected with this compiler, where the idea was to collect all the data from all the people in the world. It was a bit naive at that time. Whenever they compile and run programs, we could collect all this data, we could build models on the fly, and we could actually make a self-optimizing, self-learning compiler. So what could possibly go wrong with that? So at that time, I thought, wow. So when I built this system, I thought that we would solve all world's problems. Once again, I can retire probably at that time and enjoy my life and spend time on doing research. What I didn't realize, so when we released this compiler, first of all, it was a great feedback from the community. We got lots of downloads. And in 3 days, I collected more data in the repository than during 5 years of my life, of my research life. And that was, I remember, we were very excited by the results. We thought that, wow, it's working. But then, unfortunately, we started seeing many issues with reproducibility. What we didn't realize is that trying to move machine learning to production compilers, we have to deal with continuously changing systems every day. So our software hardware is changing every day. And this is what is the big difference with academic research and production, that the compiler which we're testing in academia and we're spending 2-3 years training it and so on, when we moved it to production, so programs were completely different, data sets were completely different, things were changing every day. So we just couldn't reproduce most of the results which we collected. We couldn't capture information about all this changing environment. And at the same time, just when we realized that we need to have a system which would be easily kind of extensible, so the idea was maybe users could share benchmarks and data sets, we didn't have this, so it was impossible to improve it. And our results were becoming very quickly outdated. And when we started looking at other papers and we wanted to connect, there were many papers being published at that time on machine learning for compilers and for hardware. We couldn't actually implement them, compare them, because also, again, there was no shared code and data, or if it was shared, we couldn't have apple-to-apple comparison because people were using completely different metrics and so on. And at that time, I remember that I got kind of depressed, and I thought that, oh my God, I will actually, from all these ideas of 10 years of work, what can we do with that? But then something else happened. So because we released all the code and data to the community, suddenly, maybe 2-3 weeks later, I started receiving very nice feedback from the community by saying that, oh, you know, we tried to reproduce your results, we didn't manage, but we actually fixed your code. And they started sharing, some colleagues started sharing patches, some colleagues started sharing data sets, some colleagues started sharing features. And I suddenly realized at that time that actually by maybe releasing this code and first kind of failing in reproducing some results, but bringing community on board actually really opened up many new interesting opportunities in our research. And at the same time, in 2010, 2014, what happened is many other colleagues started feeling the same problems. And just to mention a few interesting initiatives, so Christian Kolbeck from Arizona did a very interesting study at that time. So he looked at 600 papers And his team wanted to check if code was shared, and if it was shared, if it was possible to run and build it, to build and run it. That was called weak reproducibility. And they showed that majority of papers either didn't share code, or even if the code was shared, it wasn't enough, so we couldn't build it on new machines. And on the other side, my great colleagues from the program languages community, they decided to change this problem and to solve it by introducing so-called artifact evaluation at several programming languages conferences like PLDI, UPSLA, and so on. And the idea there was to, whenever you publish your paper, but before it's being released to the community, so you have 1 month and the community is trying to reproduce the results. And if the results are completely reproduced, the code is nicely written and so on, so you get a badge saying that this paper was validated. And that's what they call strong reproducibility. And I suggest you to have a look at a few links, which you can see here, to see the history of this artifact evaluation, because it was a fantastic initiative. From my side, at the same time, I wanted to not only just to put a stamp on the paper and show that the results are reproduced, but I actually wanted to learn how we can make it easy to reproduce papers and how we can connect with production. So how we can make it easy to validate research in production. So at the same time, I started slightly different artifact evaluation, and I would like to thank Bruce Childers and Shriram, Krishnamurti, and a few other colleagues who actually supported this initiative. We started slightly different process. We wanted to work with authors and help them pass artifact evaluation, and so it's kind of a supportive way of, if you have a problem with your code, and even if you release the code and we couldn't reproduce your results, we help you to reproduce results, and at the same time we learn what is wrong during this process, and the idea was to see maybe how we can automate the process. And it worked out pretty well, and we introduced this process in 2015. And just to say that at the same time, I wanted to actually say thanks to ACM, who realized that at this moment we had many different initiatives going on in different conferences, and everyone was trying to do slightly different ways of doing artifact evaluation, or understanding badges, and so on. So ACM decided to organize the task force on reproducibility, and they connected many people from different conferences, and we tried to come up with a unified way of badging and common ways of reproducing papers. So once again, you can see the links because it's still an active group, and there are many interesting things going on. And at the same time, the idea was not just to have one badge, but to give multiple badges. So if you just share a code, but the results were not reproducible, we still give you a badge, like saying that your code or data is available. Because once again, in my research on machine learning and systems, it's very important to have really much more data sets and benchmarks. That's what is missing. So by promoting, just like if you share your code and data, it's already a fantastic community effort, and we want to give you a badge for this. And it worked out pretty well, and the ACM Digital Library also started providing search facilities so that you can actually go there and see papers which were reproduced, and you can search them by those badges. There were a few other initiatives which I also want to mention, that SIGARCHA is now working on the very interesting checklist for empirical evaluation, and there is an emerging group on reproducibility. And of course, there are recently some very great initiatives at New RIPS, and papers with code, and some other initiatives. But saying that, from my side in 2015, I did something extra. So I wanted to document the process. So whenever the paper is going through the artifact evaluation, I wanted to unify this process. So I introduced unified artifact appendix and the checklist at the time in 2015. And all the papers which were going through my artifact evaluation, the artifact evaluation that I organized, all had the same appendix which describe your software dependencies, hardware dependencies. That set dependencies, what is your installation procedure, what is your experimental procedure, and the notes if someone had problems with reproducing results and how we can improve it. And it turned out that in the past 5 years, once again, it just turned out that I reviewed 150 papers, which has this artifact appendix, and you can find them either in digital library or in the few links which I show here. But the interesting part is at first I was really scared because it was really deja vu that all this, what I just told you before about the MILEPOST project, I saw all those problems again. That first of all, in machine learning and system research, artifacts are extremely complex and diverse and changing all the time. So we have to deal with the latest FPGA, with GPUs, CPUs, software is changing. So it's actually very difficult. It takes sometimes 1 month to actually just prepare the setup, run experiments, and collect results. Sometimes we have actually cloud with multiple nodes, supercomputers, and it's actually really difficult and time-consuming just to even prepare and run results, and even before trying to see if there is a match with a paper. And what is worse, what we realize that there are no any common formats or API for the shared artifacts. So if we have 150 papers passing through artifact evaluation, we would have 150 scripts for building the code, running the code, collecting the result. And there is no kind of knowledge reuse between different artifact evaluations because everyone is writing their own code. What we also realized that just sharing code and data or Jupyter notebooks obviously is not enough. Because most of the time our nice evaluators, they want to test it within a slightly different setup, maybe with a different compiler, maybe on a different hardware. And this, again, it's really lots of manual effort. We also realize that containers obviously are very useful, but they're not enough because once again, in our domain, you want to try results on your system very often. So you want to try it with your new compiler or maybe with a different library, with a different CUDA version and so on. So containers is a nice snapshot, but it's not really helping you to adapt to the latest software and hardware or to changing software and hardware. And the same problem with apple-to-apple comparison. If everyone is writing their own scripts and they're spitting some results and numbers, how can we trust them? How we can actually compare them and so on? How we can compare papers? So at first, I have to admit that for the first year or two, I think I was a bit lost, and I thought that I didn't see how we could sort out this mess, and it was tricky. However, what I noticed that probably with this artifact appendix, I started analyzing multiple papers, and I think after 30 or 40 papers which went through, I started seeing some commonalities. So first of all, I realized that most of the papers or researchers, when they share their code, actually, even though there are so many ad hoc scripts, we're using the same actions. So most of the time, we want to compile a program, run it on a different system, we want to detect the system, we want to install some packages, we want to collect data, perform some statistical analysis, plot graphs, some of these things. And furthermore, those actions are usually just applied to slightly different objects. So if you want to install, I don't know, instead of GC, you want to install LLVM, or you want to download ImageNet with specific version. So those actions are applying to common objects, which maybe have some common meta information. So we can kind of potentially maybe unify it. And we can see that if you install packages, you would have some meta in configuration, compilation, linking, and so on. So that's where I started thinking that why not to convert all those ad hoc scripts into some microservices with a common API and common meta information. So the idea was why not to have some, let's say, Python module, which would call program and which would have two functions, compile and run, which would unify all the shared scripts so that you could start reusing the same script and the same module instead of having like thousands of scripts out there. And in such case, we could actually provide those small microservices for all those common tasks. And there are not so many common tasks. If you look at, there are maybe 10 and so on. And at the same time, we could actually convert those objects into, we could provide some unique ID for them so that if someone creates an object somewhere that you start, like whenever you move it somewhere, you always have a generate unique ID, so you can actually find and trace this object as soon as it's live. And you can provide some meta information and provenance, let's say in JSON or YAML, so that we can apply those actions to those objects from different projects. And that's how 5 years ago I decided to create this collective knowledge framework. And what is funny, that it was just a prototype. At that time, I already didn't think about changing the world. I just wanted to see how we can solve this crazy problem with reproducibility. And so I created this simple Python framework where basically you could share your research project, if it's GitHub or GitLab or Bitbucket, with a very simple structure. So with your first level directory, it would be describing your action, your object or an action, and second level will be actually having a wrapper for your object, and the third level directory will provide you meta information. And CK was just providing a common API so that you can actually consider those projects as a database of objects. And in such case, whenever you pull your GitHub or whatever repository, you get it from zip, star archive, and so on, you can actually start listing your objects. Let's say you have common programs, or you can search data sets, you can add your own data sets, and it becomes a common format across many different projects. So we try to provide a common APIs and common meta information for different projects, and with minimum changes, so it required minimum changes to your projects. Next, what we're trying to do is that I started looking at all the papers which I was involved in analyzing and reproducing, and I listed most commonly used actions, and it turned out that the very first 4 actions which we had was pretty simple. You want to describe your target operating system, you want to detect information about your platforms, you want to detect software which is already installed on the system. Why? Because you actually want to adapt to your environment. So you want to share recipes, let's say, to find that maybe ImageNet was already, it's a huge data set, maybe it was already downloaded on your system, so you don't want to install it, you don't want to change paths or play with paths, you want to automatically detect it. If you have a compiler, you want to automatically detect multiple compilers. So we started sharing automation actions and recipes to detect those different software which you may use, which we saw in those research papers. And the same, we were installing missing packages. Again, all these research papers which I looked through, we just tried to see what packages we use, and we started sharing recipes for detecting and installing software. And of course, afterwards, with years, we provided more information about like recording experiments, performing statistical analysis. So it was always shared as microservices, as CK microservices. And just a few things that at the same time as we had a simple Python API, so that it's very simple. It's dictionary input, dictionary output, so that even if you're a researcher, you often forget very complex API. So here I wanted to be as simple as possible. And this dictionary input, dictionary output API actually really make life easier, and it brought, I would say, DevOps principles to research and to sharing. Whenever you share your projects, you can actually really start sharing it with common APIs, and you can use DevOps principles to this. And just a couple of more things. So what is interesting now is that when you now deal with your experiments, when you implement what we say workflows, let's say program workflow, which can compile and run program, what it becomes is a Python module which actually queries CK as a database. And it basically, whenever you give it some benchmark, it would read its meta information from your repository. It loads it. It will resolve dependencies. It will try to detect all your software, what is needed. It will install missing packages. It will run program and compile it, run it, and unify results. But the whole point for this kind of treating your research project as a database was that now whenever we have different papers shared in the same format, and it can be GitHub repository, it can be Docker image, but with the same CK format inside, It can be private repository, it can be Jupyter Notebook, which querying database. It becomes kind of a plug-and-play format, so you don't need to spend your time on checking like hardwiring path and so on. So since it's a database, so whenever you compile or run program, you can actually start sharing benchmarks, data sets, models in the common format, and it picks up automatically. So this really simplified our life considerably, and we could reuse actions between different research projects. And in fact, when you get a project, when you reproduce paper and you get a project in this format, between papers, you already have the same API. So actually don't need to spend time really looking through README, understanding what is this code, what it's doing, how to use it. So you always use the same API. So it's really provided you kind of a front-ended API, plug-and-play API to your research project, so that evaluators, it takes them it's much simpler for them to actually test your code, run it. And if there is a problem, they send you a feedback, and we can start improving shared components, and we can improve them, and then the community benefits from the same reusable components. And that's why I call this project collective knowledge, because the idea was to actually really bring community on building such kind of reusable blocks from our research papers. And at the same time, as I mentioned, the idea now is that whenever I want to run it on a completely different system, I can automatically adapt to it. So because I can detect all your environment and run code specifically on your environment. What is interesting is that besides that, it's actually brought DevOps principles to our research. Why? Because now whenever you have a common API and meta description, it was much easier to actually start using continuous integration services and so on your GitHub repositories if you share your research code there. And you can integrate it with other services and so on. But it also, for those who are unfamiliar, a few years ago, there was a new initiative saying that we need to have FAIR principles for data. And this FAIR principle, it says that data should be findable, accessible, interoperable, and reusable. And here, basically, because we provide an API and we share all the code and data as a database, and we provide meta information and unique IDs, we actually follow these FAIR principles, but we also not only look applying FAIR principles to data, but also to code. And that's why I add one more thing, which I think is missing, that it should be portable. So we provide also portable code and FAIR principles. And at the end, naturally, what happened is that the community, when I talked to the community about this, we said that we actually need to have a platform where we could start sharing all those components from reproduced papers, and so that everyone else can find them and try to reuse them. And that's what happened with the Synology.io platform, which I developed some years ago, where basically it's a big database of those reusable components, workflows. We have dashboards which are connected with workflows, so that you can run experiments collaboratively, and you can actually see, you can perform automatic validation of your paper, and if there is some unexpected behavior and anomalies, you can actually see it, and you can discuss it with your evaluator, with the community, what happened there, and collaboratively improve shared components. Here I will now go pretty quickly. What I want to tell you is that with this approach, we realized that now, actually, after so many years, so what it took me now 15 years from my first research project, I suddenly realized that having all those components, I can actually really get back to my original research on applying machine learning to systems. Why? Because now we have all those basic blocks with meta information. So with the community, we can actually start exposing all the information about features, choices in your system, and it's full stack optimization. So we can expose optimizations and features from the compiler, from a program, from a model. We can start unifying the information which we collect, like metrics and so on, and we can start modeling the behavior. So here, the few funny stories is after reproducing first probably 30 papers and getting those components from there, the very first thing was to I implemented this auto tuner, which I spent, which failed 15 years ago. And I just wanted to see if I can implement it now with those basic blocks. And thanks to the Raspberry Pi Foundation, I discussed this project with Eben Upton, and he's very interested in making it much easier for students or for young generation to understand computers. So it was interesting for him about if we can use this approach to optimize Raspberry Pi devices. And it was a 3-month project. And now I wanted to test if instead of 3 years, which it took me to build the MILEPOST project, if we could implement this from those blocks, from reproduced papers in 3 months. And we did that. And I don't want to spend much time now discussing, but you can actually look at this project in those links, and you can actually try the shared code. Because when we released it, the community tried it, and we collected, once again, lots of results from the community in just a few weeks. And the results were reproducible this time. So we were keeping all the provenance. People could take the same workflow, rerun it, share results, and adapt to the new environment. So with time, what was really great, what didn't happen with MILEPOST project, that all those papers, when you share now with those workflows, you can actually start running it with a completely different compiler, with a new compiler, with a new hardware, slightly different hardware, slightly different data set, and it will still run it, it will still collect results, and you can analyze it, and you can start applying machine learning to this. So just a few more things, why it improved the quality of research now, and why we became much closer to production. So the very first thing which we did is that we tried to reproduce results from the MILEPOST project, which was 10 years ago. And there we saw the same results. So with those few benchmarks, which you can see here on the right, basically the graph here shows you speedups over different benchmarks. And what is shown with the red line is the few benchmarks which we use for the paper. So speedups were not very high, but the prediction rate was, as I just showed you, 87%. It was good. It was matching results. With the community, we shared more than 200 benchmarks. And just as you often see with machine learning papers, when you have fantastic result with accuracy and you move it to production, the results, the accuracy drops. That's what we saw too. But I didn't say that the project is bad. I just showed you that when we publish papers and we don't actually try it in production, we use a few benchmarks, that our result can be really far from reality. It just proved it. But what is great now with the reproducible workflow, the community started playing with this workflow, and they started improving the shared workflow. And here was a fun example that ST Microelectronics, colleagues from ST Microelectronics, they tried this workflow, and they found a very interesting case that in one of the small code, this is very simple code, what you can see, it's a image threshold filter. They realized that in some strange optimization happens that in one of the shared examples, we had an anomaly. We had a very nice improvement, 17% improvement. What I realized through my research career is that very often you actually, okay, you see this result, but you actually don't, if you're in compilers, you don't often look at the data set. You don't try to see what happens there. So you can apply deep learning nowadays. You can apply machine learning and try to figure out what is the features of these experiments. But in fact, if you look at the shared result and you look at the images, you would realize that this code was used in the surveillance camera. And when you are using this surveillance camera during the day, then you kind of have many changes in the picture. And obviously, the if conversion is useful when it depends if your if statement is taken or not often, so you can do some optimization. So if it's during the day, the behavior is kind of random, so you don't see any change. But overnight, most of the picture is black, and you have only some white kind of changes, so you would have this improvement. So your feature would be, if you use deep learning, you would have very costly analysis of features. But in fact, it's just a very simple feature like time of the day. So if you actually look at the experiment you shared, you would add this feature and it would separate those cases. So this community effort of finding features was actually a really interesting experience. It's really like collaborative effort of improving your results, which again, if I published paper and I didn't share all those results, I would never even come to this. 10 years ago, I didn't see that. And just a few more things. When I started talking to my colleagues about this project, they told me, oh, but can we look actually at deep learning and can we reproduce deep learning papers with this paper? So we started reproducing more and more deep learning papers, and we started sharing components for most commonly used frameworks out there, most commonly used data sets, models. And the idea, once again, that we could reuse exactly the same pipeline which was shared once. So we could reuse it and start just plugging in different components for deep learning. And what was interesting is a few years ago, I visited my colleagues in the University of Washington, and they were very interested in this project and said, why not to create a tournament where we want to optimize machine learning software hardware stacks for image classification, let's say. So colleagues could share anything, any workflow, it can be with any framework and so on, but then we convert them to CK format. And we share results, we can have apple-to-apple comparison, and we share results on the CK frame, on the Synology platform. And we find the winners. So the idea was, again, bringing the community to actually optimize machine learning and software and hardware stacks. And it worked out very well. So we teamed up with ACM Digital Library, which was, once again, thanks to them. They were hosting this tournament, and they also provided us a way of sharing artifacts. So you can go to this link and you can see all the artifacts shared in the CK format. But there was something else interesting with such kind of experience, is that when we shared, now you can go online and you can actually start playing with those results which you collected from different users, but you can also start looking at really not just accuracy or, let's say, speed up, but we started collecting lots of different metrics which you can expose in a unified way. So you can start looking at the Pareto frontier, and if depending on your scenario, you can actually really find the best solutions. And just to keep it short, one of the results was, one of the submissions was from Intel, and they showed really great results on Amazon WS instances that you could get really very high throughput with ImageNet classification. We reproduced those results, they were fair, and what we found out that a few months later, Amazon colleagues contacted me and they said, oh, you know, we just actually took this result, what you had, and we generated a Docker image, we ran it in Amazon, and it actually showed the same results. So we actually provided it as one of the images in Amazon, and we did the talk with them about this result. So it just showed you that this common way of sharing workflows with your paper allows you to really start using it in production. And they also connected with SageMaker, and it was really an interesting experience to see that not only we can reproduce the paper, but we can actually start using it in production with those workflows. I will start skipping it very quickly. So there were two other extremes that IBM asked us if we can provide this, reuse exactly the same workflow for quantum computing. So we did some really fun hackathons in Paris and in Cambridge and Oxford on the same framework was used, the same workflow was used to generate, to run different systems on quantum computing, and we found some actually really completely new designs. So not we, our participants found completely new designs which were reused afterwards in companies. And on the other extreme, we created an Android app where we could actually start collecting, running ML benchmarking across hundreds of machines, and we had really many participants, and over 3 months, I collected once again more data than in 5 years of my PhD life. So it's really enabled this collaborative way of experimentation. I go very quickly here. I want to mention just a couple of more slides because we're running out of time, and then I will conclude. a few interesting cases for such kind of portable workflows when you share workflows with plug-and-play components along with your research papers. We had a very interesting collaboration with General Motors, which had to look at co-designing efficient software hardware stacks for self-driving cars. And they actually picked up this approach so that they can look at accuracy, speed, cost, and other designs of different vendors and pick up the best solution. And you can see their presentation about this. So it was a great result. And I want to mention that this was still a prototype, what we did with CK, with Collective Knowledge. And a few years ago, there was a fantastic initiative called ML Commons and MLPerf, where a group of universities and hardware and software vendors decided to join together because they also realized the problems which I was speaking about now, and that we need to come up with a common way of benchmarking machine learning that across different hardware and software, we need to unify it and so on. And I suggest you to look at their website because I think it's really great initiatives with many people who are involved there. We were involved in an interesting project called MLCube, trying to provide an API, common API for machine learning papers. And the idea is that we want to connect it with Collective Knowledge Framework because several colleagues and several companies actually reuse the same workflow to generate many interesting submissions for edge devices there. Just to conclude, at the moment, 20 years ago when I started this research, the biggest problem was that we didn't have any code or data shared. Nowadays, we have actually really many papers who share lots of codes, and there is papers with codes, fantastic initiative which try to match papers with, connect papers with code. So we can see 30K code repositories, we have lots of data sets, shared dashboards. But what I want to say is that without having a common API, common meta information, and so on, having so many code and data shared without any format is as bad as probably not sharing any. And we really need to come up with a common infrastructure and with a common way of some kind of portable and reusable workflows with plug-and-play components. And my hope is that what I wanted to tell you today, just my experience with research papers is, first of all, the biggest problem with reproducing research papers now is that just some basic thing that we have to do so many modifications of shared Python code or scripts and so on, hardwired paths, just to start system running. We have to get away from this, and we probably need to look at the projects as kind of database, and that's what we showed at CK, that we can do it. We need to provide common APIs and meta information for shared artifacts, because in such case, we can start sharing we can start reusing many benchmarks and data sets out there instead of like always fixing them and trying to understand how to connect them. The same, we shouldn't have hundreds of projects shared and hundreds of projects have their own scripts and so on. I hope that we'll start reusing the components and scripts. And the same, we need to have workflows that adapt to continuously changing software and hardware. So Docker or Jupyter notebooks, they're great, but they're not enough. So we really need to have this information. And we need to have an apple-to-apple comparison results. Again, it helps. And I want to mention that CK framework is just a prototype. So I'm now scared about saying that we solve many issues because it's actually still evolving. And I hope that we'll get, with the community, we'll continue improving such kind of concepts. And my view is that in the next 3, 4, 5 years, I hope that we will see papers shared with portable workflows that can kind of plug and play all the components, and we can validate results automatically and move them to production. And it's not a buzzword, but I believe that having this kind of system with DevOps principles and FAIR principles will really improve the efficiency of machine learning systems, and we can actually really accelerate innovation and enable open science. And it's not a buzzword because over the past 10 years, even though I sacrificed my research life by focusing really a lot on reproducibility, on the other hand, the best part of it was that it allowed me to work with so many great people over the past 6, 7 years, and I just wanted to kind of list some of them. And it was basically their feedback and discussions that gave me this idea of building this framework and continued reproducibility initiatives. And there are many links which I want to say thank to so many people who are actually involved in this project. And I hope that we'll continue community effort to solve reproducibility issues. There is still a lot to be done, only scratching the surface. And here I want to stop and just say thank you for listening to me. I hope it will be useful. And I will be happy to take questions if there are any. So thank you very much.
Thank you very much, Grigori. Great talk and great work in an important area for everyone. This is really one of those areas that benefits everybody in the field. Let's move on to Q&A. We have probably more questions than we're going to have time for, so I'm going to sample them. One of the questions is, how does your work deal with platform variability? Result run on machine X needs to be reproduced on machine Y. How do you see that being made manageable?
So two things. So first of all, the workflow, our workflows, they can adapt to a new machine, and then we can detect the environment, we can install missing packages, and we can start running code. It doesn't mean that the code will run, because if your system is completely new, we can fail, but again, we're collaboratively improving the code. When we run it, we usually apply statistical analysis, so we run code several times, and I didn't speak about this, but I applied some statistical analysis for analyzing the variability. If you have different frequency, you run your system with different frequency, we consider them as features. So we're actually trying to match if you have a variability in your experiments. We're not saying, oh, it's a red flag. We're actually trying to analyze the result because it's reproducible, and we're trying to see what influenced it. Sometimes we see that, oh, you run with a different frequency again. You have some cache effects. So we're actually collecting all this unusual behavior, and we're exposing it to users, and we're trying to solve it and find features which influence this variability. That's my view how we can solve it.
That makes sense. Sort of a fingerprint match, and then get your closest fingerprint. Another question is, when do you think reproducing a result really makes sense? When should someone go to the trouble of doing that?
Interesting question. So let's say, when I was in academia and I look at many interesting papers, one of the sad things, what I think, is that we have many interesting papers being published. There are too many papers being published. I'm very sad to think that if we don't reproduce papers, or we reproduce too many, we can miss interesting papers, and we can miss interesting techniques. So my ideal case is that in 2-3 years, all the papers, my hope, will share their results in a common format. So in such case, we'll not be having this question, which paper we should reproduce or not. It will be automatic. It will be a side effect. So it shouldn't be like enforced. And that was my hope, that eventually we'll reproduce all papers.
I hope that we achieve that brighter world.
I hope. I think if we join together, maybe with the Malcolmans too, I think we can hopefully advance that field.
And a field as empirical as this, I think it's going to be crucial.
Yeah.
Do you see any challenges as more and more results are run on very large systems? Is there a way to achieve some level of reproducibility for this type of effort?
So first of all, I want to mention that I was recently less involved in reproducing results on large systems, and I was more involved in actually reproducing other side results on smaller systems. From what I see, and particularly actually being involved in MILEPOST, is that let's say that the problems are completely different from, let's say, inference and training. So if you have a really large system, you would start looking at your networking result, your network, your load on many nodes. I don't think it's really very big difference. The problems that you still need to criteria to find those problems, what breaks your reproducibility. And again, in our case, when we provide your workflow, the idea, just what I said in the previous question, is that if you see a problem with reproducibility, it's not like you put a red flag. Let's figure out what happens and expose this feature in this information for our workflow so everyone can actually take advantage of this. So I'm not saying what can be done. I think I provide the recipe in the future that we can solve it with this kind of portable and customizable workflows. But I don't have an answer. I think it will be a collaborative effort.
Fantastic. Someone asked, and they used the word competitors, but I think given the importance of this problem, let's call it, collaborators. Do you see there as being other people out in sort of the reproducibility space producing useful tools?
There are very many related and interesting tools which are now being developed for reproducibility, and unfortunately, I didn't mention them, but what I want to say here is the following. So first of all, I want to mention that I was very interested in tools like MLflow, kubeflow, SPAC, EasyBuild, Popper, lots of tools which can actually solve parts of the problem. What I want to say is that I really want to avoid competition at the moment. What I see as a problem in past years of my research is that everyone wants to write their best software and try to dominate the world. I think we really need to have a collaborative effort. And this idea of what I did with collective knowledge, if you notice, it was really providing APIs for different tools. I'm not competing with tools. I was trying to really connect them. So if you have your own tool, I don't want to compete with you. I want to provide an API so we can reuse it, take value of this, and if it becomes fantastic and it dominates others, it's fantastic. But I want to connect them all together. And I really hope, once again, with those initiatives, Papers with Codes, ML Commons, ACM, that are bringing different people together, that we will avoid having too many tools, that will try to kind of connect them instead of competing. This is my hope.
I think that's a great hope. If we could have, sort of a common basic approach and let everyone build complex infrastructure on top of it, that would be fantastic. Do you see any use case around sort of improvement of results, where you're sort of tracking the progress of a result that people are working on over time, or do you treat them as sort of discrete points?
I think with the papers which I was looking at, there were not so many papers where I could answer this question. So they were pretty discrete at the moment. So I can't say. What I see is that, once again, this I refer to Papers with Code project, where they try to share SOTA dashboards, and they try to track different papers on how they improve over time. And I think there we see this improvement, but it's the missing part in Papers with Code is that you can't actually run the code and match the results. So I hope that by connecting this kind of work, what we're doing with, let's say, Papers with Code, with some other similar approaches, we will be able to track improvement. It's not there yet, and I think it's very important for the future. So it's a future work.
Fantastic. Someone is thinking big and asks, do you have any plans to take this kind of reproducibility approach to areas beyond ML, different forms of performance measurement?
So first of all, I want to mention that, and again, I didn't mention in this talk, that there are many fantastic efforts in other fields, in biology, in other fields, that are tackling different problems, and they're doing fantastic work. And I'm not trying to kind of jump and start solving their problems, because they're actually solving really many interesting efforts. Once again, I think we will converge to common tools in the future. And I was discussing it recently with the biology community, and they were working a lot on workflow frameworks, and they said that nowadays there are 100 different workflow frameworks out there which are trying to solve reproducibility. So I hope we'll kind of converge to the common framework, but I'm a bit scared of jumping to other domains because I think there is lots of other effort going on in parallel.
So within the domain, what do you see as being like the sort of 3 big obstacles to great reproducibility? Like if you could wave a wand, what would be the 3 things you'd like to see changed? Or features added to your framework, anything like that?
Very first thing is this adaptability to software and hardware. So what I said, what differs us from other fields, I think, is that we're dealing with changes in software hardware which are there every day. So Docker, Jupyter notebooks, and so on, they're great, but they're not solving this. So my thing is that we need to have an extra layer which adapts your experiment to continuously changing systems. This is one first big thing. I'm trying to solve it with CK, but it's just a scratching surface. There is still a lot to be done. This is one thing. Second thing is this problem that we're not reusing any code. We're not reusing actually what I would call as automation actions. So everyone is writing their own code and so on. This provides we have technical debt, we have lots of issues, so we can't have apple-to-apple comparison. So we need to get rid of this. This is the second thing. We need to reuse code and data as much as possible. And what is third is probably we need to have vendor support, let's say, from hardware vendors or software vendors, which would expose more features and choices in their systems. One of the big problems what I had with let's say, with improving performance of compilers or hardware is that it's black box. And hardware vendors or software providers, they do not want actually to give you an access to it. And in such case, having this black box approach, it's a problem for reproducibility. We need to really have a support from developers to expose all those features, characteristics, and so on, because then we can actually, it's the third thing, we can improve reproducibility considerably. So those are kind of very quickly 3 big things, what I can list.
Fantastic. So unfortunately, we have run out of time and then some, and there's still a fantastic set of questions. So I think beginning the talk, we talked about some of the ways you need your questions answered offline and continue the discussion. Please avail yourselves of those. Thank you very much, Grigori. This talk was recorded. It will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities there as well. Also, please take a minute to fill out our quick survey and suggest future topics for speakers. On behalf of the ACM, Grigori, myself, thank you all very much for joining us and for all the great questions. Hope to see you at future talks. And virtual round of applause for Grigori and all his hard work to make things reproducible. So, well done.
Well, thank you. Thank you for listening. Thank you very much. Take care.